Sometime in the next few weeks, the machine engineers have spent nearly a decade building is going to leave Earth and head for a spot nearly 1 million miles away. And when it gets there, it's going to start doing something no telescope in history has ever managed to do at this scale. It's going to hunt for hundreds of thousands of planets. It's going to photograph over 1 billion galaxies. And it's arriving months ahead of its original deadline in an industry where flagship missions almost never show up early. This isn't a concept. This isn't a future plan. The fuel is already loaded. The countdown clock is already running. This is the Nancy Grace Roman Space Telescope, and if you haven't heard much about it yet, that's about to change. Hubble gave us our first real window into deep space. James Webb gave us the ability to look further back in time than ever before. Roman is about to join them as NASA's third great flagship observatory. And once you understand what it's actually built to do, you'll understand why astronomers have been waiting for this launch for years. Let's start with the date. Roman is scheduled to lift off on August 30th, 2026, riding a SpaceX Falcon Heavy rocket out of Launch Complex 39A at Kennedy Space Center in Florida. That date matters more than it might seem. NASA's original requirement was for Roman to be ready no later than May 2027. Instead, the mission is launching roughly 8 months ahead of that deadline, a genuinely unusual outcome for a telescope this complex, especially after watching James Webb slip years past its own original timeline before finally getting off the ground. So what exactly makes Roman worth this much attention? Picture a primary mirror the exact same size as Hubble's, 2.4 meters, across. On its own, that's already a serious, capable telescope. But Roman pairs that Hubble-sized mirror with a camera roughly 100 times wider in its field of view than anything Hubble has ever carried. Think about what that actually means practically. Photographing the entire Andromeda galaxy in full detail would take Hubble dozens of separate images, carefully stitched together afterward. Roman can capture the same view in a single shot, without giving up any of the sharpness that made Hubble famous in the first place. That combination is the entire reason Roman exists. Webb was built to zoom in, staring intensely at individual, carefully chosen targets, to extract every last detail modern instruments can pull from them. Roman was built to zoom out, sweeping across enormous sections of the sky quickly and repeatedly, catching things a narrow, deep view would simply never notice. Astronomers sometimes describe it as the difference between a telephoto lens and a wide-angle lens sitting in the same camera bag. Having both tools available at once, rather than choosing one approach over the other, gives scientists an entirely new way of studying the universe. If a mission like this genuinely gets you excited, go ahead and hit that like button. Right now, it costs nothing, and it helps get this in front of more people who love this stuff exactly as much as you do. Now let's talk about what Roman is actually going to find, because the numbers here take a second to fully process. Scientists expect Roman to discover somewhere between 60,000 and 100,000 new exoplanet candidates using the transit method, watching for the faint dip in a star's brightness as an orbiting planet crosses directly in front of it. For comparison, humanity has confirmed roughly 6,000 exoplanets total, across every observatory and every research team combined, over several decades of dedicated searching. Roman alone could end up finding many multiples of that number. But transits are only one piece of Roman's planet-hunting arsenal. Its real specialty is a technique called gravitational microlensing, and it works in a genuinely strange way. When a foreground star happens to drift directly between us and a much more distant background star, the foreground star's own gravity bends and magnifies the light coming from behind it, acting almost like a lens floating in space. If that foreground star happens to have a planet orbiting it, the planet's gravity adds a small, brief extra flicker to that magnified light, revealing its presence, even though the planet itself is never actually visible. This method can catch worlds nothing else can find. Wide, distant orbits, small rocky planets, and even rogue planets drifting completely alone through the galaxy, untethered to any star at all. Roman's dedicated microlensing survey will stare continuously at a dense field near the galaxy's core, monitoring hundreds of millions of stars simultaneously, checking for these brief brightness changes every 15 minutes, across repeated observation seasons stretched over roughly 5 years. Researchers estimate this single survey could reveal well over 1,000 new cold exoplanets, a meaningful fraction of them smaller than Earth, worlds essentially undetectable by any other current method. On top of that, Roman also carries a coronagraph, a specialized instrument built to block out a star's blinding light so any planets orbiting it can actually be photographed directly. Direct imaging of exoplanets has only succeeded a handful of times in the entire history of astronomy, because it's an extraordinarily difficult technical problem to solve. If Roman's coronagraph performs the way engineers designed it to, It could capture some of the sharpest direct images of exoplanets ever taken, a genuine technology demonstration for the kind of instruments future missions will need to eventually photograph a true Earth twin. If you're enjoying this one, now's a good time to hit subscribe, because there's a lot more space content like this coming. Planets are really only half the story, though. The other half of Roman's mission tackles one of the biggest open questions in modern physics: dark energy, the mysterious force apparently causing the universe's expansion to accelerate over time. Roman is expected to observe more than 1 billion galaxies over its mission, along with detecting tens of thousands of type Ia supernovae, a specific class of stellar explosion astronomers use as reliable cosmic distance markers, essentially mile markers, scattered across billions of light years. By carefully tracking how light from these explosions has stretched and shifted on its way to us, researchers hope to finally pin down exactly how dark energy behaves, and whether its strength has stayed constant across cosmic history or shifted over time. This is genuinely one of the biggest unresolved questions in physics today. Dark energy is currently estimated to make up roughly 70% of everything in the universe, and scientists still don't fully understand what it actually is. Roman represents one of the most ambitious attempts ever made to gather enough solid data to finally start answering that question with real confidence. Roman won't be working alone either. It joins a new generation of wide-field survey telescopes reshaping modern astronomy, including the European Space Agency's Euclid mission, already mapping billions of galaxies to study dark matter, and the newly operational Vera Rubin Observatory in Chile, conducting its own massive, repeated survey of the southern sky. Together, these instruments form a coordinated network, each covering different wavelengths, different regions of sky, and different timescales, giving scientists a far more complete picture than any single telescope could ever provide alone. Getting Roman ready for this moment has taken years of careful grinding work. The observatory has been shaken violently to simulate actual launch vibrations, blasted with extreme sound to mimic liftoff, and cycled through brutal temperature swings inside a vacuum chamber to prove it can survive the environment of deep space. It arrived at Kennedy Space Center by barge in late June 2026, and on July 25th, engineers finished loading 290 gallons of hydrazine fuel into the spacecraft, propellant it will rely on to reach its permanent home at the second Sun-Earth Lagrange point, a stable location roughly 1 million miles from Earth, about 4 times farther out than the Moon. Once it arrives there, Roman will begin its primary science mission, planned to run at least 5 years, though NASA's own history suggests missions like this one frequently run far longer than their original timeline. If Roman follows that same pattern, its eventual discoveries could dwarf even these already enormous early projections. The sheer volume of data this mission is expected to generate is staggering on its own. Roman is projected to produce roughly 20,000 terabytes of data over its lifetime, an amount so large that entirely new data processing techniques are being developed specifically to keep pace with it. And that flood of information won't just sit in an archive. Roman's wide, repeated scans are specifically built to catch transient events as they happen, supernovae detonating, black holes flaring as they feed, turning astronomy into something closer to a continuous, time-based science rather than a series of isolated snapshots. That shift matters more than it might initially sound. For most of astronomy's history, telescopes have captured single frozen moments, individual glimpses of a universe that never stops changing. Roman's ability to revisit the same patches of sky again and again means scientists will finally get to watch entire regions of the universe evolve in something close to real time, rather than piecing together isolated observations collected years or decades apart. That continuous monitoring is exactly what makes microlensing detection possible at all, since those brief planetary signals last only hours or days and would vanish completely from a telescope that wasn't already watching closely. Roman is also expected to turn up surprises much closer to home. Scientists predict the telescope could identify hundreds of previously unknown moons scattered around Jupiter, Saturn, Uranus, and Neptune, small faint objects that have simply been too difficult for existing telescopes to spot. It's a reminder that even after centuries of studying our own solar system, entire populations of objects are still hiding in plain sight, waiting for an instrument sensitive enough to finally notice them. None of this happens without an enormous coordinated effort behind the scenes. Roman is managed at NASA's Goddard Space Flight Center with major contributions from the Jet Propulsion Laboratory, the Space Telescope Science Institute, and industry partners, including major aerospace and optics manufacturers. International collaborators, including the European Space Agency and research institutions across Japan, France, and Germany, have contributed components as well, making Roman a genuinely global effort rather than the work of any single country alone. There's something fitting, too, about the name attached to this telescope. Nancy Grace Roman served as NASA's first chief astronomer, and she's widely remembered as the driving force behind getting the Hubble Space Telescope built in the first place, decades before it ever launched. It feels appropriate that the observatory carrying her name is now preparing to extend Hubble's legacy, built around a mirror to the exact same specifications, while reaching considerably further than anyone imagined possible when Hubble first launched more than 3 decades ago. As the countdown continues, anticipation across the astronomy community keeps building. This isn't simply another satellite joining an already crowded orbit. It's widely considered the next great flagship observatory, standing alongside Hubble and Webb, each one built to answer a fundamentally different question about the universe. Webb looks deep into the past. Roman is about to look wide across the present, cataloging planets, galaxies, and cosmic explosions on a scale nothing before it has ever attempted. If everything goes according to plan, the years ahead could bring a genuine flood of new discoveries, previously unseen rogue. Planets drifting silently through the galaxy, newly confirmed moons circling the outer planets right here in our own solar system, and real answers about the force quietly accelerating the expansion of everything that exists. Roman isn't just another telescope joining the lineup. It's a machine built specifically to challenge what we think we already know, and if it performs the way scientists expect, it may end up reshaping our understanding of the cosmos just as dramatically as Hubble did more than 3 decades ago. If this has you counting down the days right alongside NASA, make sure you're subscribed with notifications turned on. Because when Roman finally reaches its post 1 million miles from Earth and sends back its first images, you'll want to be here for it.